All right, listen up here, guys. If you recall, one of the most important things we have to be able to decide about a question that involves work energy theorem is what type of energy is being changed. All right. In this example, we have a slingshot that's going to be aimed straight upwards. Anytime we're dealing with up and down, what is most likely the energy type that's going to change? Most likely it's going to be potential. All right. So the slingshot is pulled straight back, which in this case would be down. All right. 0.4 meters using 1,500 newtons of force. Okay. Now, the rock reaches a height of 30 meters. What is the mass of the rock? Okay. When it's at its maximum height, how fast is it going? Right. Drew's got it. 0. Right? When you throw something up in the air at its maximum height, that's the point where it's turning around and coming back down. The whole way up, it slows down, slows down, slows down, comes to a stop, and then begins to fall. All right? So at its maximum height, it doesn't have any kinetic energy. All of its energy is potential. How did it get that potential energy? It got it from the slingshot. The slingshot got it from the work you did in drawing it back and stretching it. All right, so work is a change, in this case, in potential energy. All right, so if I was to do this, I would go, first off, force times distance equals m times g times h. I'm not even going to put in the minus part, or the final and minus the initial part, because I don't need to. I'm only dealing with the final height here anyway. Okay. Do I know F? Yep, 1,500 newtons. Do I know D? 0.4 meters. That's how far back it was drawn, right? Okay. Do I know H? Right? 30 meters. And do I always know little g? Yeah, it's always 9.81. So I know everything except mass. Can I solve for it? All right. So divide both sides by g times h. Okay, and we're left with mass. All right, so when we do that, we'll have our 1,500 times 0.4 over 9.81 times 30. Okay, when we do that, we should get 2.0 kilograms. All right. Now, I have had a question like this on a unit exam in the past, and I made it a two-part question. First, I had people calculate the mass of the rock from the potential energy information. And then I asked, how fast is the rock going when it leaves the slingshot? Okay. Now, right now you're going, oh crap, that sounds like it would be really hard. Okay, but is it? You already know how much work you did to this slingshot, right? When the thing first leaves the slingshot, all of its energy is what? Is all kinetic. So all you would have to do for the second part is set this up, except instead of m times g times h, you would have 1/2 mv squared. All right, and so I would go FD equals 1/2 mv squared. I just calculated m, so I know all of this stuff except for v. And all I would have to do is go over half of m, okay, and then square root to get v. All right, question like that, I'm asking both types of work energy theorem questions in one question. I would only have one question on work energy theorem on the exam then. Okay. The problem with that is if you don't get the first part right, it is very difficult to get the second part right. Okay, and I just didn't feel that that was fair. All right, so I changed it and I end up making it usually two parts. Okay, or sorry, two separate questions. Everyone follow how that would work? Okay, I mean we can actually plug in the numbers and see what it would come out to here. All right, so 1,500 times 0.4, okay, divided by 0.5 times 2, which would be 1, okay, and then square root that. All right, so it would have been moving at 24.5 meters per second when it left the slingshot. All right, is that making sense, guys? Do all of these work energy theorem questions work exactly the same? Yeah, all the potential energy ones work the same. all the kinetic energy ones work the same. It's force times distance equals 1/2 mv squared, or it's force times distance equals m times g times h. The only thing that's different between questions is what did the question ask you to solve for? Force, distance, mass, or height. Okay? That's the only thing that can change. But the initial setup of every one of these is the same. So once you know how to do one, you should be able to do them all. There's really not that many tricks I can throw at you. No, work energy theorem, it gets more complex. In physics 20, we deal with questions where both kinds of energy are changing. In practicality, it's the same method. You just have a change in kinetic and a change in potential. It doesn't really, it's just a little more math. It's the same idea. Okay. All right. You guys try example 10 here. Okay, I'm going to give you a couple minutes on example 10, and then we'll go through it together. So, 4,000 joules of work is done on a 25 kilogram box, carrying it up a ladder from a height of 7 meters. What's the final height of the box? Okay, so again, work is being done. What kind of energy is being changed here? Potential, because it's going up the ladder. All right, so work equals the change in potential energy this time. So that's going to mean m times g times hf minus m times g times hi. Everybody okay with that? Right? And since I know what the work is, they gave me the number, right? I should be able to manipulate to find hf. Right? This would be about the only trick I might be able to throw at you. Okay, it would be a question like this where you actually had a value for both. Okay, final and initial. If I want to solve for this, it's part of this term. So I need to move this term first. How do I get rid of m times g times h? Move it over to the other side. Add it. Right. I'm subtracting it right now. I can move that whole term because it's really just a number. All right. So that's going to mean work minus m times g times hi equals m times g times hf. I want hf by itself, so what do I do now? Right, divide both sides by mg. Here's where most people make their mistake. They go, oh, mg on the top, mg on the bottom. They cancel. Do they? They do not. Okay? It's like the tops in brackets. You have to do it first. You cannot cancel those mg's. All right? You could if it was mghi over mg, then you could, but there's another operation here. Okay? So we can't cancel those mg's this time. All right, so when we plug this in then, plug in our numbers, we're going to have, what was it, 7,000 joules? 4,000 joules. Okay, so 4,000 minus the mass, which was 25 kilograms. Okay, 25 times 9.81 times the initial height of 7 meters, okay, divided by 25 times 9.81. Okay, we're plugging that into our calculator. We got to be careful about what order we write it in. Okay, the first thing we want to do is 4,000, okay, minus 25 times 9.81 times 7. All right, there's, okay, the final potential energy. If I divide that now by 25 times 9.81, okay, I get that it's gone up. I got a different number there. I must have punched something in wrong. Oh, I should have added it. Yep. Okay. Sorry, guys. Pressed the wrong button here. Okay. Plus 25 times 9.81 times 7. There we go. Nice big number now. Okay. Now we divide that number by 25 times 9.81. And we should get 23.3. Okay. That would be about as tricky as I could give you, and I have never given one that tricky on a unit exam. Once in a while on a quiz, okay, but not on a unit exam. Okay. Does that make some sense there, how we do that? Drew, question? It is so. All right. Yeah, I want you to try this one. It's just like the last one we did, except this time it's kinetic energy instead of potential. Question? All right, let's have a look at this one here. So it uses a spring to propel it along a level floor. The spring is compressed 0.23 meters, and the cart increases in speed from 1.2 to 3.1 meters per second. If the cart has a mass of 650 grams, what force is needed? So we're changing the kinetic energy, but here's the trick. Okay? It gives you a mass in grams. What do you need the mass to be in? Kilograms. Okay? Most people get this question wrong. They lose 1 mark for the answer because they forget to convert the grams to kilograms. Okay? So, here's what we've got to start with. Work is the change in kinetic energy. All right? And from there, okay, we're going to go this. FD equals 1/2 mvf squared minus 1/2 mvi squared. Right? And we're trying to solve for force, so I'm going to divide both sides by what? By what? By d, right? Okay. If I divide both sides by d, I've got F all by itself over here. All right. So here's what I've got to do then. Force equals 1/2 times 0.650, okay, times 3.1 squared minus 1/2 times 0.65 times 1.2 squared divided by how far we pulled it back, which was 0.23 meters. All right, so alright, so there's the top of my equation divided by the bottom. Okay. Oh, what did I mess up here? No, I don't need to square root. I put in 650. I must have missed the decimal button there. Okay. Alright, 0.5 times 0.65 times 3.1 squared. Okay, sorry guys, minus 0.5 times 0.65 times 1.2 squared. That's better. Divided by 0.23. Okay, gives us 11.5. Alright, so we used 11.5 newtons of force in order to get that. Okay, so you can see punching it into your calculator carefully is pretty important. I've screwed up the last 2 because of punching something in wrong. Alright, so make sure when you check it that your answer makes sense. I mean, right away I knew my answer didn't make sense. Alright, so when you look at it, okay, double check those kind of things. Caroline, question? Well, but you were calculating the force. You didn't have the force before. And see if you get the same number as you get here? Yes. Yeah, you could. All right. Everybody with me on that one? Okay. All right. I would like you guys to finish up what's left on that worksheet. And those are the last few examples that I had there. Okay, so let's finish up that worksheet because you know that Tuesday's quiz is going to be exactly like what's on here. Going to be like yesterday's quiz as well. Okay, so let's make sure that we are ready for that one.